Hello. So let us wait for others to join, at least three, four people. Then we'll start. Maybe 5 minutes we wait. Is that all right?
Okay.
Okay. So, good afternoon, everyone. This is week 4 of the problem solving session, Saturday class. So, let's start already. Okay, so today's problems will be mainly focused on the LS coupling in, in the electronic system. So, with our first question being, what is the spectroscopic term symbol of hydrogen in its ground state? So, please let me know what you think. Any guesses? Okay, 2s half. Sorry, 2 2p half. Which one is it? P or S, and why? Anyone else? Okay, so to describe an electronic system, you need many things, right? For example, you need specific energy, wave function, and you need the electronic configuration. You also need the total angular momentum, spin, and their relation, their interaction. If there is an external magnetic field, then how the intrinsic magnetic field of the electrons, how they interact with the external magnetic field. You need all of that, right? So you know that earlier when Bohr started studying the structure of atom, he just used the term n to describe an electron. N is just the, the which number of orbit around the nucleus is the electron in. N is equal to 1 means the closest one. 2, 3, 4, gradually the number of orbits increase. So, but then it was seen that this is not enough. Okay, so whenever you have a charge which is moving around, in a circle, it constitutes a magnetic field, right? So that means even for the case of electrons, they move around, they move in circles. This is the nucleus. The electron goes around like this, right? It is moving in a circle. So that means this also, uh, this constitutes, mm, this gives rise to some magnetic effect. So the electron, and so there are also other electrons around it, right? So all of the electrons have an associated magnetic moment, isn't it? There is an angular momentum because of this rotation, and this constitutes, you can say, mm, this gives rise to some magnetic field. Okay, so you have the total angular momentum, and also, okay, you have, let me just write, you have the total angular momentum, orbital momentum, and spin momentum. All these information, these are also required to describe spin is because of, you know, the electronic spin. So you need all of these parameters also to completely describe an electron. Okay, so from here, you know, we have the L and S terms. Okay, the orbital and the spin momentum. Okay, so and these two cannot be separated. Okay, so the total orbital momenta is, you know, right, summation of all the orbital momentum of all the electrons. Similarly, total spin S, S is bold. Okay, summation of SI. Okay, now so what is my total angular momentum? Sum of these two. Okay. So my total angular momentum is what? Sum of this J is equal to, J is my total angular momentum, is L plus S. Okay, this is a vector sum. Okay, so you see this J is equal to L plus S. This gives rise to a specific energy level of an atom. Okay, if you put in the individual values, you will get something called a term symbol 2s plus 1 Lj. Okay, this is known as the term symbol, and this identifies, or it specifies, this specifies an energy level of the atom. Okay, due to the coupling of the orbital and spin momenta, we have a total angular momenta which is different for different, electronic states. So here, what is S? S is the spin of the electron, okay, and this term 2s plus 1, this is called the multiplicity, okay, spin multiplicity rather. So what does this tell us? The number of spin states associated with a given electronic state. Okay, and what is L? Okay, so this L is just the total orbital angular momentum. Okay, you know L is equal to, it can be 0, 1, 2, 3, 4. So these stand for, if it is 0, we have S, 1, P, 2, D, then F, G, H, and so on. Okay, you can see that this code almost matches that which is used for atomic orbitals. Okay, okay, you also have a J term. What does this stand for? The total angular momentum. You can say angular momentum quantum number. So now what was our question? We want this particular term symbol of a hydrogen, of an electron in a hydrogen atom in its ground state, right? So we have to just write something, 2s plus 1, L and J. Okay, so S for 1, there is 1 electron in the ground state of hydrogen atom, S is equal to 1. So S is equal to half. So 2s plus 1 will give you 2. Now L is the angular momentum, right? So for ground state of hydrogen, there is only 1 electron. So ground state, only 1 electron, right? And this is obviously in an s orbital. Okay, so that means L is equal to 0. Therefore, total angular momentum, summation of Li, there is only 1, so this is 0. That means 0 stands for S. So this will be S. And then what about J? J is just L plus S, which is half, right? So what will be our spectroscopic term symbol? That is 2s half. I hope this is clear.
Yes, ma'am.
Okay, now uh, you know that this is also called the doublet state. Okay, because for this half here we will have mj is equal to plus minus half. Okay, so the ground state has a degeneracy of 2 because this total angular momentum, this can have a z axis projection of plus half h cut or minus h cut by 2. Okay, now this is why when uh, when we studied the Balmer series of the hydrogen atom, they from the n is equal to 3 to 2 level, they were expecting a single line of transition. Okay, but they saw there are two. So this is just because of this reason, because of the spin orbit coupling. Okay, so now let us go to our next question. Write the term symbols and their degeneracy for the electrons in the given orbital configurations. there is some internet issue from my side today. So if at any point you see that the video is frozen, please let me know instantly. So, any answers? Okay, before you think about it, I would like to ask you something, that what is this number 1, 2, what are these?
Principal quantum number.
Yes, exactly. And what is this one? The SPL, angular quantum number. And what is that? You know, this superscript 1111.
Means the ground state.
No, this one just means that there is just one electron. Okay, this is the orbital configuration. Mind that. These are written in orbital configuration. Okay, just like when we say that some atom has the atomic number is 23 or something, or is 13, and you start writing 1s2, 2s2, like that. This just stands for that, nothing else. So what we are interested in, the term symbols. Okay, let's start with the first one. So it is a 1s1 electron, right? And I'm just writing our usual notation on the top right corner. This one, right? So you can see, okay, you might have asked what is the purpose of this, of like we have this 111 written. Okay, fine, it's one electron. So what is the use of that? The use is here. So just half cross half cross 2 plus 1, that is 2. So for all of them, 2s1 plus 2s plus 1 will be just 2. Okay, because there is just one electron. So 2. Now L and J. For the first one, you can see the information for L is already given. Okay, S, that means L is equal to 0, right? So, but in this notation we just write S. Okay, now J. So for this one L is 0, S is half, therefore J will be half. So 2S half. Okay, and what will be the degeneracy? Mj, that will run from minus J, then J plus 1, and so on, J minus 1 till J, isn't it? So the number of mj's gives you the degeneracy, right? Of this particular energy state. As I told you, every term symbol denotes one particular energy state. Okay, so the degeneracy will be, so for this we have mj is equal to plus minus half, degeneracy 2. So let me make a table. If I have my orbital configuration in the first column and then the term symbols and then degeneracy, so the first one is 1s1, so my term symbol is 2s half, degeneracy 2. So what about the next one, 2s1? In a similar fashion, you can see that our multiplicity will be 2 and this will be S as usual, and J here again L plus S, so half plus 0, that is half, so again half. Okay, so and mj plus minus half, so degeneracy 2 again. Okay, the third one, 2p1, again we'll follow the same. So our multiplicity is 2. Okay, and L, right? So here L is what? 1. Are you guys following? Okay,
Yes, ma'am.
so L is 1, right? So of course it will just follow whatever is written there. Now the main part is J. Okay, J will be this one, total 3/2, right? Now there will also be a half, isn't it? Why is that so? Can you tell? So my term symbols will be 2p half and 2p 3/2. Okay, yes, so why do we have two terms, 3/2 and half? Because J runs from L minus S to L plus S. Okay, and I mean L minus S plus 1 and so on and forth. Just keep on adding plus 1. Okay, for our previous cases we just had one term, minus S and plus S. Okay, because our L was 0 anyway. But here we have L1. So we get half and 3/2. So now what will be the degeneracy? Yes, what will be the degeneracy? For the 2p half, for this state, it'll be 2, because again, for the 2p half state, what will be mj? Plus minus half, so you have 2. And for the 2p 3/2 state, you have mj 3/2, half, minus half, and minus 3/2, right? So our degeneracy is 4. Sorry, it's looking really messed up, but I just highlight the answers. That is 2 for the first one, 2 for the second one, and for the third one, which is number C, it is 2 and 4. Okay, corresponding to the two energy state, because as I told you, each term symbol defines one particular energy state. Okay, so this particular energy state 2p3 by 2, this has 4 degeneracies. So if we apply, so this ls coupling, is splitting them up, it is lifting the degeneracy. Okay, so the third one, 3s1, you can see once again the term symbol will be just 2s half. So the principal quantum number really doesn't affect the term symbol, isn't it? Think about it. Let us complete this exercise and we will see, does it affect it at all? So term symbol will be 2s half. And once again, for the 2s half state, degeneracy is always 2. You know that. Now the 3p1 state. 3p1. What will this be? Again, it will be as we've seen for the 2p1 state. Okay, because basically over even here L is 1 and S is half, so you add them up and you will see you'll get same 2p half and 2p 3 by 2. Okay, again the degeneracy will be 2 and 4. Now 3d1. What about this? Yes, here L is equal to 2. Okay, so again multiplicity will be just 2 because 2s plus 1, and L will be just this. Now what about just J? What will that be? So once again, L plus S. So 2 plus half, that is 5 by 2. And you'll also have a 3 by 2 term. So 2d 5 by 2 and 2d 3 by 2. Okay. And the degeneracy here will be for the 5 by 2 term. For J is 5 by 2. You can see MJ will be what? 5 by 2, 3 by 2, half, and then minus of those, right? So degeneracy is 6. And for J3 by 2, as we have seen earlier, degeneracy is 4. Okay, so I will highlight these once again. So that's it. That's our table. Is it clear?
Yes, ma'am.
Okay, then let's go to the next one. What will be the term symbols for electrons in sp configuration? Okay, for your note, the LS coupling is also known as the Russell-Saunders coupling, okay, or the RS coupling. Okay, so yes, what will the term symbols for electrons in sp configuration? Okay, you're saying it will be 2s half, 2p half, and 2p3 by 2. Is that? Okay, for sp. Okay, okay, notice one thing compared to the previous exercise that we did. We are talking about one electron. Okay, I had highlighted and showed you in yellow, talking about this one. Okay, these ones. So we just had one value of, spin here. But in this problem, you can see, this is not a very, straightforward question. Okay, that's why I chose this question, because it helps you understand the difference. If I had just written, okay, uh, what will the term symbols for two electrons in this state and this state? So that's a very flat question. But this one is given sp configuration. That means there are two electrons involved here. So we have to think a little differently. Okay, let me write that for you, because for the others who did not join today, if they see this video later on, it will be easier for them. So two electrons are involved here. Yeah, here. Okay, because I have mentioned that this is in sp configuration. So for the electron in the s state, L is equal to 0, right? And S is half. For electron in p state, okay, here I will write L1, S1. So for the p state, L2 is equal to 1 and S2 is equal to half. Okay, value of S is, fixed. That is, this is a, you can say, inherent property of electrons, the quantum property. Therefore, what will be the total LL here? Sum over Li. Okay, that means L1 plus L2 to L1 minus L2. Okay, so this is 1 to 0, which is, oh sorry, which is basically just 1. And S total spin angular momentum. Sum over Si, that is S1 plus S2, S1 minus S2, absolute values. So you have half plus half, 2 half minus half. Okay, that means 1 2 0 1 0. So you see, you have two values of S here, 1 and 0. Now what? So let us go to our usual notation, 2s plus 1, and you have L and J. Okay. So for s is equal to 0, what do we have? 2 into 0 plus 1. And okay, what will be L here? See, what we got, the total orbital angular momentum is 1, right? L is equal to 1. So that means this is P. Okay. So I write P here, and J. And so what will be J? Hi Sushmita, thank you for joining. Can you please mute yourself because I'm getting some, okay, thank you. Okay, so yes, this J will again, it will go from, J will go from L plus S to L minus S. Okay, L is 1, so 1 plus 0 to 1 minus 0, basically just 1. So for S is equal to 0, we just have one term symbol, which is 1p1. Now for S equal to 1, because you see our other value of S, sorry, not this one, was 1. Okay, so what will be 2s plus 1? That is fixed. So this is 3 2s plus 1, and as you know, the orbital angular momentum, that is p. Now J will vary, because again you can see in Ellis coupling, J is from L plus S to L minus S, so that will give 1 plus 1 to 1 minus 1, right? So this is 2 2 0 2 1 0. Okay, so here we will get 3 terms, 3 values of J. J is equal to 2 1 and 0. So 2, then 3p1 and 3p0. Okay, so our final answer is, for the question that what will be the term symbols for electrons in sp configuration, the answer is 1p1 and 3p. Either you can write this together like 210, or you can just write them separate. Is that all right? So the previous one we were talking about just one electron, okay? But here we're talking about the interaction of two electrons. So we need to consider the spin of both the electrons. Okay, so let's look at our next question. What are the allowed electron transition lines for the given, not lines, but states? Given energy states. Five lines. Okay. Is it? What about the others? So I'm just writing the Russell-Saunders selection rules for electron moving from one atomic orbital to the other. You must be knowing already that the selection rules for an electron moving from one atomic orbital to the other are Okay, these are the RS selection rules. Okay, that means LS coupling. Del S 0, del L is 0 or plus minus 1. Sorry, my taskbar keeps popping up. Del J is 0 plus minus 1. However, the J is equal to 0 to J is equal to 0 transition is forbidden. Okay, and del M J is 0. This here again, MJ 0 to MJ 0 is forbidden. Okay, so now tell me, one. Okay, next I got one line as the suggested answer. Let's see if any of them is correct. Okay, tell me, will this transition take place? 2d5 by 2 to 2p half. What is it here? This is my J, right?
Yes.
So del J is 2. Is that allowed? No.
No.
So this is not allowed. Then what about this one?
Not allowed.
Not allowed. Yes. Then okay, so that means no transition line from 2d5 by 2 in this system? No. Okay. According to the selection lines, no transition from 2d5 by 2. Then let's check 2p half. Okay, so I can see only one possible transition. So here are the selection rules satisfied. Del J is 0 and
Yes.
yes. So this is okay. Del L is also 0. So yes, only one line. This is the correct answer. Is that clear for the one who joined later? Shushmita? Okay, I hope so. Let's go to the next one. What are the allowed electron transition lines for the n is equal to 2 to n is equal to 1 states in the presence of a magnetic field? Once again, let me add a term here. Presence of an external magnetic field. Okay, since we don't have much time, so I will straight away start with the explanation. You can understand that we are talking about the Zeeman effect here. Okay, so now, uh, there are two kinds of Zeeman effect. One is the normal, and the other is the anomalous. What is the difference between these two? The difference is, when Bohr and all were checking out the transition lines of electrons, they found that when there is no magnetic field, of course you have already learned it in your theory classes, but I'm just giving a gist of it, okay, just to refresh your memory. So when there is no magnetic field, that means Bz is equal to 0, then is equal to 2 to 1 state, right? So this is 2p, say, and this is 1s. So without any magnetic field, there'll just be one transition as expected, just from a higher energy state, because as you know, energy is increasing in this direction. So yes, just one line. But when you apply a magnetic field, so Bz is not 0, then you will see that this 2p line will split up, right? ML term, because P is 1, P means L is equal to 1. So ML, once again according to the selection rules, so it will be 2p plus 1, 2p1, 2p0, and 2p minus 1. Okay, and you have your 1s state here. So now you will have 3 lines. This was the normal Zeeman effect. Just you put an electron in a magnetic field, and this external magnetic field is interacting with the angular momentum of the electron, and accordingly it splits, or it lifts the degeneracy in the individual energy states. But later on it was seen that there isn't just 3 lines, there are more lines. Okay, So let me just write that there are more lines. Why is that so? Because, as you know, even a revolving electron has a magnetic field. So we cannot forget about that. There's a spin of the electron. So the spin angular momentum, the orbital angular momentum, even they are interacting with the externally applied magnetic field. So there is a greater number of lines which we can see. These, even this 2p1, 0, 1, minus 1, even these are split into finer energy states. Okay, so in this case we had, or from your derivations and all, I'm not going into that. So you just have the total energy of the system as E is equal to En, whatever is your principal, quantum number, plus Eh cut Bz Ml, okay, by 2me. This is the Zeeman energy. This extra term. Okay. Now you know that this Eh cut by 2me. This, what is this called? The Bohr magneton. Okay, this is taken to be the fundamental magnetic moment, mu b. Okay, the fundamental magnetic moment. Okay, so this has definite value, 9.2732 multiplied by 10 raised to the power minus 24 joules per Tesla. Okay, so yes, so our expression reduces to En plus mu b Pz Ml, isn't it? Now next it was seen that even the magnetic field of the electron, the spin angular momentum, the orbital angular momentum, that is the total angular momentum, that also interacts with the externally applied magnetic field. There is Ellis coupling. Okay, so the MJ degeneracy, that gets removed due to the interaction with the external field. So now, instead of just ML, we just have a slightly modified version. This is an anomalous Zeeman effect, where E, rather the average E, to generalize it more, we have En plus GMJ, then mu B Bz. Okay, so just this one Instead of this, we have G, M, J. Okay. So, you know that for LS coupling, G is given by 1 plus J, J plus 1 plus S, S plus 1 minus L, L plus 1. Okay, 2J, J plus 1. Okay, so because of these changes, we will have the Mj term now, and the degeneracy in Mj will, because of LS coupling, we have the Mj term, which gets removed when we apply an external magnetic field. So, you see we have n is equal to 2 to n is equal to 1, right? Once again, let us make a table. Do I have enough space? Okay, try to manage. Fine. So, let us have a quick table here. Term J, L, S and Mj. Okay. Just for a reminder, we had n is equal to 2 to n is equal to 1. 2 to 1. So we will have a 2p3 by 2 term, just as we had done earlier. Okay, remember this one rather. So I'm not explaining that right now. So it's 2p3 by 2, and then you'll have a 2p half and 2s half term. Okay, again these are term symbols. So you can clearly see J is 3 by 2. Here J is half, and here it's half again. L is 1. Here L is again 1. Here L is 0. S, of course, single electrons we are talking about. So just half, half, half. Now Mg. As I had said earlier, L plus S to L minus S. Okay. So you can see for the first case, what is the maximum value? 3 by 2. Okay, so it will run till minus 3 by 2. So in between, half and minus half are there. Similarly, for 2p half, only two terms, half and minus half. Again, for the 2s half term, we just have two terms. Okay. So now let us draw the diagram. So you see, without LS coupling, these would not split. It would be just 2p3 by, without, in the absence of a magnetic field. To S half here. When you switch on the magnetic field, this will split up to 4 levels. And this one into 2 levels, as we have already seen, and S also 2 levels. Okay, 3 by 2, half minus half, minus 3 by 2, again half, minus half, half and minus half. Yes. So once again, you'll apply the selection rules and just quickly write them down. 0 and del J plus minus 1, 0. What were our terms? And S del S 0 and del Mj plus minus 1 and 0. Okay, so quickly the transitions. So let us start from this line, from the 2p minus half. So will it come down to this one? Let us see what is del mj for this. That is half minus of minus half, that is 1. Okay, so yes, we will have this transition. Next, will we have this transition? Again, minus half is the final one, minus of minus half. Yes, we will have this one too, so 0. Okay, plus half to half, similar reasons, we will have this one too, because del m is 0 here. And this one, again, yes, del m is minus 1 here. Similarly, this transition, will we have this one? Let us see, half minus of minus 3 by 2. So half plus 3 by 2. So no, we won't have this. Isn't it? Okay, what about the next one? Okay, I got confused. Yes, will we have this one? Okay, I'm just drawing from what I have. Just let me know if, if there is a discrepancy, just add and check. If there's any discrepancy, let me know later on. Okay. So from the minus half line, I think both, again we'll have it going to both lines, and from the plus half line, again we have both of them. Now the 3/2 line, it will have only one transition. Okay, this line. Okay, so how many total lines do we have? 10 lines. I hope this is clear. Now next, so in whatever we have been doing till now, this is a problem based on that. Let us do some math here. Okay, so in a normal Zeeman effect experiment, the spectral splitting of the line at the wavelength 643.8 nanometers corresponding to the transition 5(1D2) to 5(1P1) of cadmium atoms is to be observed. The spectrometer used has a resolution of 0.1 nanometers. So what is the minimum magnetic field that is required to observe this splitting? Okay, so you know, due to Ellis coupling, you have this kind of terms here, but those have some degeneracy. So unless you apply an external magnetic field, these lines won't split. Okay, splitting of the spectral lines in the presence of electric field, what is that called? We have been only talking about magnetic field split, right? Under an applied electric field, what is that called? Anybody? That is called the Stark effect. So splitting of electron transition lines in the presence of an external electric field is called the Stark effect. Okay. So what about this problem? So you see, as I had written earlier, the Zeeman energy, okay, this particular thing, okay, so this is the, let me just write this as the Zeeman energy. So what is the information that is given? We have a wavelength, okay, we have a lambda given. Very good. Lambda is equal to 643.8 nanometers, and there is a resolution. Okay, let's see how to use this resolution later on. The spectrometer has a resolution, so what can this be? It cannot be, you see, it's a spectrometer, right? So what are you seeing? The wavelength. Okay, so that means this resolution is talking about the smallest wavelength that can be detected by this spectrometer. Okay, and this equals 0.01 nanometers. And what they want is B. So what I've done is, okay, before that let us see what all do we have from this equation, from the associated equation. Mass of electron, we already know. Sorry, this was ml, sorry. Okay, so mass of electron, we already know. He, we know that. Bz, we have to find. And this one, P to D, that is just 1, right? Del ml is 1 here. Because D to P, right? So, this E, we will write it in a form which includes the wavelength. Okay? So E is h nu, as we know. Let us equate this to the equation we have, Pzml by 2me. Okay, h nu is equal to Eh by 2 pi Bz by me. H cancels out, sorry, missed out the 2. So this is Ebz by 4 pi Ne. Okay, nu. Still we don't have lambda. So lambda c nu is equal to c. So nu is equal to c by lambda. Okay. Okay, this would be del nu because this is the Zeeman energy, which is the split. So similarly here, if we have to, take del nu in this equation, just do the derivative, that is del lambda, isn't it? So we will put this value here, del lambda c by lambda square is equal to EBZ by 4 pi ME. That gives del lambda is equal to lambda square by C EBZ by 4 pi ME. Okay, now we will put the values that we have, that is 643.8 nanometers. Convert it into meters. This is square. C, you know, speed of light. Nothing is mentioned, so let us just take 3 into 10 raised to the power 8. Charge of electron 1.6. Okay, BZ. This B you have to find, and you have 4 here, pi is 3.14, and the mass of the electron 9.1 into 10 raised to the power minus 31. So solve for B, and yes, so this will equal to del lambda, which is our resolution, 0.01 nanometers. So 0.01 into 10 raised to the power 9 is equal to this whole thing. Okay, so from here, what is the value of B that you get? Let me know after solving this. Okay, this ML, I think I gave a wrong explanation. This, we'll just take it 1, not because of D and P, okay? Just because we are taking the smallest, you know, this is a Zeeman split, this is a Zeeman energy, del E. So just between two consecutive MLs, okay? Just one step ML, that's it. Okay, so please solve this and let me know. Okay, so the value that I have here is 0.514 Tesla. Hope it matches with what you've got. If not, let me know. Okay, so is this problem clear? Is there any doubt in this? If not, we'll move on to the next one, the last one for today. So again, problem on Ellis coupling. A hydrogen atom is in its 3D state. So what are the possible values of J? I hope you guys are solving this. So what does 3D state mean? You have n is 3, right? The principal quantum number, and the L value, SPD, that is 2, isn't it? Okay, so possible values of J. L plus minus S. S is half. We're not talking about 2 electrons and all here, so we don't need to bother about the total S and all. Okay, so 2 plus minus half, right? What does this give you? So this is 5 by 2 or 3 by, isn't it? Okay, so the possible values of J are 5 by 2 and 3 by 2. Okay, now what are the possible values of the magnitude of the total angular momentum? What will be this? The magnitude of the total angular momentum. You know that the magnitude is given by J plus 1 square root of this and h cut. Okay, so For j is equal to 5 by 2, what do you have? J is 5 by 2 and 5 by 2 plus 1 root over this h cut. Okay, so just add these up. The answer which I have here is 2.96 h cut. Hope it matches with yours. If not, let me know. Okay, and for j is equal to 3 by 2, you have 3 by 2 root plus 1. Okay, so this is supposed to equal to 1.94 h cut. Okay, so this is the magnitude of the total angular momentum. Now the last one, what are the possible z components of the total angular momentum? How will we solve this? Possible z components of the total angular momentum. The total angular momentum, remember that. Let me highlight this one. So we will add these and then just take, the z component, okay, which is, what it is. So jz is equal to lz plus sz. Okay, so that is m h cut plus ms h cut. After this, how do we proceed? What is ml for lz and ms for sz? Yes. So for j is equal to 5 by 2, you have the z components as minus 5. We will just go from minus half h cut and then plus, let me just write it as just for 6 components. And for j is equal to 3 by 2, we have 3 by 2 h cut plus minus this. That's it. Okay, that's all. So we'll end our class here. Hope to meet you all next week once again. If you have any doubt in any of the problems, please reserve it for the next class, or you can also post in the forum. Okay, so bye bye. Have a nice evening. Thank you for joining.
Bye bye.